We're looking at Gcse Physics Unit 1 Higher Tier from Ccea for 2016. And in this case we're looking at question 5. Part A. The diagram below shows a uniform wooden plank pivoted at its midpoint. Two forces or weights act on the plank at the positions A and B shown. Show by calculation that the plank is not balanced. Okay, so the plank would be balanced if the clockwise and anti-clockwise moments were equal. So what we should try and do is find the values of those and show that they are not equal. So if I identify the pivot, then I can say that the anti-clockwise moment about that pivot has a value. In this case, it's the 20 newtons that's trying to turn it anti-clockwise. So force times distance is 20 times 1.5, and that gives us 30 newton meters of moment. We should also find the clockwise moment belonging to the other side there, the 30 newton. And that's going to equal 30 times 0.8, which is going to equal 24 newton meters. So we're shown that the moments aren't equal. In which direction will it turn? Well, it'll turn in whichever direction is the strongest moment, and you can see here that it's the anti-clockwise moment that's strongest. So that is the way it's going to turn. And then it says it can be made to balance by placing an extra weight on top of one of the existing weights. Calculate the extra weight that is needed on which of the extra existing weights should it be placed. Okay, so on this diagram we should be able to place something on top of one of these stacks to make this balance. Again, it's going to obviously be on the clockwise side, so we need to find something on there that will create a moment of 6 newton meters. So something that's 0.8 of a meter out that will produce a 6 newton meter moment. So we should just list what we know. Whatever this weight is, it has to create another 6 newton meters. It has to go at a distance of 0.8 out, because that's where the current weights are sitting. And so we just need to know the value of F. So we need an equation for F here. And moment is force times distance, so F is going to be moment over distance. And 6 over 0.8 turns out to be 7.5 newtons. And that's going to need to go on top of weight B. Part B starts off with some straight bookwork. What is meant by the centre of gravity of an object? So, centre of gravity is the point where the weight of the object appears to act. Diagrams below show a forklift truck with a load. Diagram A shows the position of the centre of gravity of the forklift truck and load with an X, and you can see it marked there. Okay. Diagram B shows the load in a raised position. In this position, the forklift truck and load are stable and are not likely to topple. On diagram B, mark with an X the new position of the centre of gravity of the forklift truck and load. Now, because they've said it's stable, this position of the original centre of gravity is going to move sort of diagonally, because this load being raised will drag it away from that position. But it is not going to pass the front pivot here, because it says that it's still stable. Okay, so we would expect it to still be inside this front pivot. Okay, so I take it away from where it was a little bit, maybe up there. So something like that. Still inside the pivot, but over and up a bit from its original position. If I'm totally honest, I don't think it should move sideways, only vertically. but the mark scheme says over a bit. Part C. To investigate the principle of moments, the apparatus shown below was set up. The meter rule, which is 100 centimeters, is pivoted at its midpoint. A weight F is placed 20 centimeters along from the pivot, and another weight of 5 newtons is placed at distance D from the pivot, so that the meter rule is balanced. The experiment is repeated for different values of F, and the distance D is adjusted until the meter rule is balanced again. And a graph of the results for F and D was plotted as shown below. And what this graph is basically showing us is that the force of one, if you increase it, then the distance of the other, in order to get it back into equilibrium, will also have to increase proportionally. The relationship between D and F is shown below. That D equals K times F, that's like a Y equals mx. Using data from the graph, find the value of K. In your answer, give the unit for K. So K equals D over F, so just taking a pair of values from the graph itself. For example, 16 over 4 is going to give us a value of 4. And since we're dividing centimeters by newtons, it's going to be centimeters per newton. Part 2. If the value of the force F was 14 newtons, explain why the meter rule could not be balanced. Support your answer with a suitable calculation. Well, this will be some kind of situation where if you increase to 14, there's nowhere you can place that other weight that's far enough out to counteract it. So we need to look at the graph. So if we look at the graph here, we can see that for 5 newtons, D needed to be 20 centimeters. So for 14 newtons, that's going to be like 2 5s and a 4. So the 2 5s are going to give us 20 plus 20, and the 4 is going to give us 16, which will give you the total distance that we would have to put in there to counteract that. Equally, we could just use this K value to figure out the distance. So we've got K equal to 4 centimeters per newton, and F equal to 14 newtons, and D is equal to KF, which is going to be 4 times 14. So D would need to be 56 centimeters, and what you need to realise is that you've only got 50 centimeters either side, so we couldn't put it far enough. The ruler isn't long enough. Okay. So the ruler is not going to be long enough.